Okay, it's great to be here. I can hear my voice echo, but I want to make sure you can hear me in the back as well. Okay,
Sounds good.
excellent. Right, so thanks, Dan, for the very warm welcome, and thanks to Vector for having me here. Something I learned today is that if you want to beat traffic by getting into Toronto, leave at 6 a.m. So if you're from one of the neighboring cities, Waterloo included, then it's a very pleasant drive, unlike other times of day. So 6 a.m. actually works. Anyways, yeah, so today we're going to be talking about building bridges, enhancing trust, and human-machine collaboration. And we'll get into defining some of these terms shortly as well. If at any point there are questions, feel free to either shout at me, point up your hand, or if you're on Zoom, somehow notify me that you have a
I
question.
think we'll be monitoring a little bit the Zoom channel.
Excellent, excellent. Okay, cool. So I think we're all somewhat familiar with this image. In recent years, the applications of AI-based systems has proliferated various aspects of our lives, from healthcare to transportation to finance and education. And as our dependency on these systems increases, so does the line between human and machine decision-making become increasingly blurred. So let's draw an analogy. Each of us have in our homes a series of machines that enable us to offload our physical labor to those machines. Take a washing machine or a dishwasher. Now, we interact with these machines insofar as we give them a predefined task. We expect that after some amount of processing or computation, they return an expected result. All the while, they operate safely within the boundaries defined for them, and if anything goes wrong, they fail gracefully. So they beep at us or blink or just stop. Now, it's not hard to imagine a future, or maybe even today, where not only do we offload our physically laborious tasks to machines, but also our cognitively laborious ones. And just imagine how casually each of us probably has ChatGPT or Claude, has a tab in our browser just constantly there, and we're interacting with them, and we're allowing our thoughts to be, guided, manipulated, whatever you want to call it, by these systems. So as the dependency grows, it's not hard to imagine that just as our relationship with the dishwasher is now second nature, the relationship with AI would become second nature. And we have to stop and ask, well, could anything go wrong? And of course, we know that things go wrong if you have any system, such as ChatGPT or one of its APIs, making consequential decisions and confidently giving you a wrong answer. We as users of these systems should have the ability to query its representation, challenge its reasoning, correct its answer, and all the while communicate in a shared language substrate. So despite there being a growing effort to have larger and more scalable and more performant models, my argument is that there's a subtle but also equally important, if not more, need to build the safeguards so that we can detect issues, correct the problems and suggest alternatives, and ultimately perfect our interactions with AI-based systems. And this is broadly, I'm giving an intro of my lab and then we'll get into the research as well. This is broadly the mandate of the CHARM lab, or the Collaborative Human AI Reasoning Machines lab at Waterloo. You're all welcome to visit anytime if you're around. And to speak a bit more technically, we try to address three questions. So the first one is, on the detect side, how does one assay the safety, factuality, and ethics of AI systems to foster trust in AI? Two, how does one recover from or overturn poor experiences via decisions made by AI? And ultimately, three, how does one design systems that make use of the best of both human and machine abilities? Of course, addressing these questions might also already trigger some thoughts in your head that, what kind of tools do you use? And we borrow tools and insights from several subfields of AI, including explainable AI, which aims to answer why questions and promote a conversation about systems' outputs. Neurosymbolic AI, which blends learning and reasoning for models based on interpretable and widely accessible concepts. And also causal inference, which gives us the beautiful mathematical framework upon which all of this is built. And also, incidentally, it's widely and commonly used as a model for human cognition. If you work on any of these, I'm happy to chat. But also, if you work on multi-agent systems, behavioral economics, or psychology and cognitive science, that's also very much related to the targets here. And this is an open call for collaboration. So come chat. Happy to figure out where our intersects are. Excellent. So today's talk, I'll be focusing on the second question of the lab, which is, how does one overcome or overturn poor experiences via decisions made by AI? And for that, I'm going to be spending the remainder of the time talking about algorithmic recourse. This is what Dan presented, and the results you'll see are a summary, a high-level summary, of work done over the past half decade. And as you can notice on the bottom, with collaborators primarily in Europe, because that's where I did my PhD. Of course, I'm a U of T grad and a Waterloo grad and a Europe grad. So if you get the opportunity, definitely visit there as well. Okay, so let's start with a case study. This is Edward. He's 28. He has a salary of $75,000. He's somehow, I guess this is pre-inflation, managed to save up $25,000. He's employed as a software engineer and he's single. Edward is looking to purchase a home. After months of scrupulous savings and many open house viewings, he's finally found one that he's interested in. So he must visit the bank. Now the bank may use a system such as this one to decide whether or not Edward gets the loan. Does he get the loan in this case? Yes, no, yes, no. Good, he doesn't get it. Or perhaps one like this, or one like this. And as these models become more complex, they become better able to model the nuances in the historical data set, but of course they lose out on something called their interpretability, which we'll define in a couple slides. In this context, there are other stakeholders. Stakeholders such as the bank may ask, what are the most influential features towards the decision? A regulator or governing body may ask, is the system fair by relying on sensitive attributes such as age and marital status? And individuals like Edward who didn't get the loan may ask, I didn't get it, why not? And what should I do the next time I apply in order to get the loan? Addressing these questions broadly falls under the umbrella of explainable AI or XAI or interpretable ML, IML, whichever acronym you prefer, which can be defined as the ability to explain or to present in understandable terms to a human. XAI has two broad goals. The first one being to understand why a particular decision is output, and then two, to recommend actions that would result in a desired output. And one method that, at least in the past few years, has been attempting to solve these is called counterfactual explanations, which are statements of the form, how the world would have had to be different for a desired outcome to occur. For the case of Edward, it's if your salary had been 100,000 instead of 75, you would have been offered the loan. So let's take a closer look at counterfactual explanations and see whether or not they actually satisfy the two goals of XAI. So this is Edward again, at some time t0. Edward's characteristics are gathered together into a vector. Let's call it xf for x-factual. I know it's really small, but the screen is also small, so I apologize for that. I think there might be other ones that you can look at. Anyway, so xf is the vector representing the characteristics of Edward. It can be real value, categorical, mix of all data. Some things might be missing too. And y in this case is 0, let's say, because the bank is denying Edward the loan. Now, looking back in time, at time t0 minus t, there exists an alternative Edward with a different set of characteristics. Let's call it XCFE, or counterfactual explanation, whereby this combination of characteristics on whatever model the bank is using would be offered the loan. Now, let's project forward in time and assume that the world is stationary. Of course, one can expect that the same set of characteristics would also be offered the loan. Now, I want to take a moment just to remind that one of the primary objectives of explanations is as a means to help a data subject act rather than merely understand. And there's something missing from this picture, and that is that if you want to understand intuitively, a counterfactual explanation might inform Edward where he needs to get to, but not how to get there. And so the missing link here is this one here called algorithmic recourse, which can be defined as the actions required for, or the systematic process of reversing unfavorable decisions across a range of counterfactual scenarios. And so that's what we're going to focus on. Primarily what we want to ask is, if we have access to a counterfactual explanation, can that actually constitute recourse for us, or do we need something more to actually give recommendations? So let's plot out Edward again. Now he's standing on a red dot because red means rejected. We have an arbitrary decision boundary here assumed to be linear, h theta. And of course, he's on the negative side, so he's denied a loan. The original counterfactual explanation problem was formulated by Wachter et al. In 2017 as this one here. It's an argument over some objective function here, the distance between where Edward is and some alternative instance within space. We want the prediction to be flipped, assumed binary, and we want the alternative sample to be plausible. So what does plausibility mean? It means, for instance, that at least within a population, we don't have anyone that has age negative, right? So that would be something implausible to suggest someone to have negative age. Okay, so what would the solutions look like for this optimization problem? It'd be either one of these green stars represented as these hypothetical alternative Edwards. A couple years later, Hossein et al. Reformulated this optimization problem as this one here. Again, I apologize for it being small. But really what's changed here is now we've changed the objective function from a distance to a cost function, and we have another constraint called the feasibility constraint. And this enabled us to model the world just a bit better, because if, let's say, Edward is 28 and 26 is a plausible age for him to be, but it's certainly not a feasible age for him to become, right? You can't reduce age. That's also not how our world works. So this reformulation just made it a bit more explicit as to what kind of constraints, real world constraints, we can embed into this problem. And now instead of focusing on XCFEs, we're focusing on delta and delta star, and that's the solution of this optimization. Of course, our question still stands as to, do counterfactual based recourse actions, I know that that's a mouthful, but basically is the result of this a counterfactual based recourse action? Does it yield optimal and feasible action for recourse? That's the first question. And the second one is, how does providing recourse affects other stakeholders within the system? Okay, I'm going to stop here for questions. If anything's unclear about the setting or motivation.
Do you want people to offer criticisms of that definition at this stage, or do you?
I'm open to criticisms.
Well, I mean, I guess, like, one of them could be, one of the scenarios could be get married. Or that could be the simplest one under the cost function, or like double your salary, right? And like if you offer only one option, then you may be presuming something about their their value.
Absolutely. So coming up, and this is way at the end of the slide about future work, coming up with cost functions that actually matter according to that individual are very important. You and I might both go to a bank, and I'm sure you have great credit, but let's say we both get denied, then the recommendations based on living conditions might be completely different. You're from Toronto, I'm from Waterloo, and so maybe the same recommendation wouldn't work on both of us.
Yeah.
So yes, individualized cost functions are super important, open area for research. Come talk to me if you're interested.
And another thing I'm wondering if you're thinking about already, it seems quite interesting and quite different from like what is usually studied in machine learning, is that there's going to be a feedback loop here created. If you were to actually succeed in deploying algorithmic recourse in a large scale, you would all of a sudden have the population trying to exact these changes.
Yes.
And that would potentially, mean that the kind of accuracy of the predictor for predicting loan default would now maybe stray quite a bit from where it was before.
Absolutely. So here's a concrete example of that. You're all grad students. You all apply to be a grad student at some point, and many of you, including myself, might get rejected at 1 year. And you get some recommendation from some system, that this is what you should do. Add a paper, get this reference, contribute to open source, blah, blah, blah. You come back the next year and all the applicants are stronger again. So maybe the recommendation from the prior year would not work. We'll get into some of that discussion as well, whereby my argument, at least just so you get a sneak peek, is that this problem isn't just a technical problem. It's a social problem, and we're not the only ones actually trying to contribute to it. But we'll get there. Good point. Okay, let's try to answer this first question. Do counterfactual-based recourse actions of delta stars yield optimal and feasible real-world actions for recourse? To actually answer this, we need to first review some preliminaries, and that is of causality. So who here knows causality or thinks they know causality? Okay. Who was here at Bernard's talk earlier this month? Wow, nobody. It was a full house. Where are they? Okay, anyways, Bernard was here earlier this month, and who knows who Bernard is? Bernard Shulkoff. Okay, you're all fresh grads, that's okay. You would put your hand up as you go through your degree. Anyways, let's review causality or causal inference, at least within the scope of machine learning. We're going to be adopting the framework introduced by Uday Pearl. He's an emeritus now at UCLA, and also partially responsible for Bayes nets, but then also for causal inference within machine learning. So we define a causal model as M, as a tuple of S, a set of structural equations where we define the relationship between every variable xr as a function of x parents of r, as well as some exogenous noise variables. And we also have a distribution assumed here to be factorized independent over the background variables. What does that look like? It looks something like this. I see that part of the screen is covered, but that's okay. So really, if we're trying to model the relationship between x1 and x2 and x3, then we make some assumptions as to which variables are nodes and how do the edges portray the direction of causality. And then everything else about the system that we don't care about, we dump into U1, U2, and U3 as background, outside of our system. In the case of Edward and loan, you could have, for instance, bank balance and salary and whatever be your endogenous variables, the ones in the green cloud, and other stuff like COVID and inflation and geopolitical risk and all that be outside of the system. Now, in order to actually employ causality within some of these systems, and generally to actually make inferences using causality, we need to make some additional assumptions. So those assumptions are things like the corresponding causal graphical model of the system is acyclic. Acyclic means no cycles, so they don't go back onto one another. And also we have mutually independent noise variables, meaning that there's no links between U1, U2, and U3. This is otherwise known as causal sufficiency. Now, if you ever start to work with causality, you'll come to appreciate that causal models entail in them three different types of distributions. So they entail observational distributions, interventional distributions, and counterfactual. And by nature, these three types of distributions are different. How so? An observational distribution would be me this morning asking myself, if I were to leave at 6 a.m., what is the expected time that I would arrive in Toronto? That's an observational distribution based on past historical data. Interventional would be, well, now I'm going to leave at 7. I'm going to act on the world by leaving at 7. What is now the expected time of arrival? And counterfactual would be, I left at 7 and I arrived at some time. I observed that output. Had I left at 6, when would I arrive? So there are three different types of queries, and Pearl actually puts these on what he calls a ladder of causation, corresponding to three different types of thinking. Observational is just observing the world. Interventional is acting on the world. And counterfactual is imagining something about the world. Counterfactuals are never actually accessible to us because we can't reverse time. So we only can make inferences, but we can't actually observe any. Now, Bernard, who was here earlier this month, also nicely puts this into this diagram, showing that the one on the bottom is an observational distribution, which we try to learn most of the time with generative models, right? We're not really acting on the world. We just have a ton of data, and we're trying to learn P of X. But a causal model is one that contains not only P of X, but also all possible interventional distributions within it. So these little icons here are hammers corresponding to interventions that you would perform on a world, and then what would the distribution look like? So if you have access to a causal model, and that's big if you have access to it, then you can model various types of interventions. Questions? Good. Okay, so with this preliminary aside, let's go back to our problem here. Let's throw in the numbers from the case study. We had Edward, we had the decision boundary, we had 75K salary, 25K bank balance. I'm going to add some numbers here just for the sake of illustration to the decision boundary. It's a binary classifier sign of x1 plus 5x2 minus some threshold, 225,000. But now I also have some information about how causality works, or I assume some information about how causality works in this environment. And that is that everyone who, again, pre-inflation, everyone who is seeking to purchase a home saves some percentage of their salary towards their down payment, right? So 30% of X1 at the end of every year is contributed to the account towards a down. That's an assumption I'm making. Now, if I go based on existing methods, the counterfactual-based methods that don't assume anything about causality, they'll give me two solutions. They'll give me delta here, which says increase your salary by 25K, get a raise. And the other one is, or the optimal one here, at least in terms of relative effort that he needs to exert, is increase your savings by 5 grand. Somehow, borrow from family, do whatever, increase your savings. Now, this makes no use of the causal information at all. So it's really not too difficult to come up with an alternative example, which says, if you manage to increase your salary by only 10 grand, of course it's less effort, right? Then the result of that change would also propagate towards your savings, and together that would propel you to the other side. And as these numbers should indicate, this is of course 14% is less than the rest, so it's less effort for Edward to perform. Okay. Now, in this case, I think the takeaway already is that the counterfactual-based recourse actions do not actually yield optimal actions that someone should perform in a world. Now, another thing I want to point out here is the relationship between x1 and x2 in this system is a positive relationship. One can imagine systems where the relationship is negative. So one example is, let's say I'm a big agriculture company, I'm deciding on the location of a rice paddy. Right? And we all know, at least from high school physics, that when you change elevation, temperature also changes. Right? Every 100-meter increase in elevation has 1 degree decrease in temperature. And if you don't take that causal relation into account, and if you start just giving recommendations by ignoring causality, then you'll be giving a recommendation that might not even fall through at all. Right? So I think the first part of the question we've answered already, which is that counterfactual-based recourse actions do not yield optimal actions for recourse. What about the second part? What about feasibility? So in order to address feasibility, we need to understand how actions are performed. So this is again notation from Judeo-Pearl about you have a structural causal model, and you take a variable and you assign a new value to that variable, severing all the relationships that come into that node. Given a delta star from existing methods, then we really have two choices as to which variables we want to intervene upon. The variables, again, are the endogenous ones that are blinking there. And we have two options to decide which one of the subsets of variables do we intervene upon. Either we intervene on everything, even those that delta says is 0, or we intervene only on the ones that delta is non-zero. And if you're following along, then it should probably be clear already that both of these have problems. If you only intervene on ones where delta star is non-zero, then you have consequential effects, you're not modeling, you don't know what's going to happen to downstream variables. And if you intervene on every variable, that's assuming that you can hold some variables fixed. And that's called a non-altering intervention. And unfortunately, that also is not available to us in most situations. Let's say you're grad students. Of course, grad studies take time. Your age doesn't stay fixed. We can't do that. Or maybe someone can, I can't. So anyways, both of these options are unavailable to us. And so unfortunately, the second part of the question is also that counterfactual-based recourse actions do not yield feasible actions for recourse. And this gives rise to a proposition. The proposition is, okay, we skipped over the proposition. Anyways, the proposition is, if you have recourse actions from existing methods, they only translate to optimal and feasible actions if you're only intervening on leaf variables within a system. And for obvious reasons, that's very restrictive, right? Because you have a whole world, causality plays a role, and that's going to restrict. Is it all doom and gloom? Well, we hope not.
That sounds like a sufficient condition, right? Like you're safe if you only condition.
Yes, but it's just so restrictive in terms of the possible worlds that you could intervene upon. So yes, it is a sufficient condition if you only intervene on subsets of variables, which is also the same as assuming all your variables are independent in the world, which is a false assumption, right? Okay, so what do? This is the work from Hossein et al., and we come along and we just change one of our constraints here. And instead of assuming that variables can actually be changed additively and independently of one another, we assume this complicated relationship FA, F inverse, whatever. It's really just applying the rules given to us by Pearl based on our assumption of what the causal model is. And what this allows us to do is to say that we can move beyond just the independent world assumption and now have assumptions about how causality works and bring that directly into our optimization problem, go ahead and solve it. And so there's also a discussion we don't need to get into, but we argue in our paper that maybe we shouldn't be calling these counterfactual explanations in the first place, because counterfactual is a term from causality and you're not really using that. And the better term, actually from philosophy, is contrasted explanations. And the recommendations then given by our approach would be called consequential recommendations, because they have consequences.
How should I understand these bold F maps? Have you defined these, or should I interpret them as like a projection?
So the F here is, I see now that I should have just called it S, because S is what we define as our set of structural equations. So it's really just S under some action, and then the inverse of S. And S is our structural equations, which we assume to be the model of the world. More clear?
So F inverse of XF goes back to the U variables to tell me what delivered that outcome?
Absolutely,
That
right.
could be a set, though.
That could be a set, yes. So how counterfactuals work, like I said, the example was I left at 7, I arrived at whatever time. Had I left at 6, what would have happened, right? The fact that I observed something about the world tells you something about my driving habits, my car, maybe whether it's snowing or not, right? All of that information is captured in the evidence that you have from observing me arrive at a certain time, having left at 7. So that is F inverse of XF. That means going from what I observed, XF, going back to understand or infer the background variables that led to this, my driving habits, my car, whatever. And then FA just means, well, now let's imagine a world in which I left at 6. With those background conditions, when would I arrive? So there's 3 steps to computing counterfactuals. The first one is called abduction. That's F inverse of XF. And then action, that's FA. and then prediction is putting all of it together. Make sense? Yes? Nods? No? Confused? Too scared? Okay. So, also, here's a tip for those of you who are just starting to write papers. This paper was desk rejected twice, and the follow-ups were approved and accepted and presented as spotlight, et cetera, et cetera. And now it's one of the top cited papers within recourse. So if you have an idea and if you really believe in it and if it makes solid sense, go for it. Sometimes reviewers, need a bit of encouragement to get past it. And yeah, it was quite a drama to get this through, but it's there now. Anyway, so a summary of the theory of the first proposition is that counterfactual-based actions from prior works would guarantee recourse if and only if the set of descendants of the acted upon variables is the empty set, otherwise only if you're suggesting actions on leaf variables, which we said was obviously restrictive. The follow-up work, which I mentioned got accepted before this one, says that ignore all previous works. What are the conditions under which we can actually guarantee recourse? And it turns out you can only guarantee recourse if the true model of the world is fully specified, right? So if you don't have the SCM, you cannot deterministically give recommendations for recourse. And already there should be alarm bells going off saying, well, we never have the model of the world, so what do we do? And that's fair. So in this follow-up work, we give suggestions as to how we can give probabilistic solutions to recourse rather than deterministic ones based on the fact that we don't have the true model of the world. How does it look like? There's two approaches. The first one says, this is again Edward saying decision boundary. Had we had access, oh, that's a tongue twister. If we had access to M star, which is the true oracle model of the world, then this would be the optimal action. Edward would arrive at the blue star. Now, if we don't have access to it, we can still make some assumptions, right, about what type of a family of causal models it is. So let's say that we assume that we have a family of causal models, like additive noise models, and that gives me M1 and M2 and M3. And then we can start to optimize over the actions such that in expectation over this family of models, we would still be off on the other side. And same process, right? We do, for each of these, we do abduction, and then we do action, and then we do prediction. And it turns out that this additive form works very nicely with Gaussian processes. Who's worked with Gaussian processes? Good. So you can formulate it using GPs, and there's actually a closed form to get this distribution. Now, you might put up your hand and say, well, I don't want to make that assumption either. Why are you making the additive assumption? And I'll say, well, tough luck. If you don't make any assumptions, you really can't go far in causality. But what you can do is you can say, I'm not only going to look at Edward, but I'm going to look at other 28-year-old software engineers with whatever bank balance in Toronto, right? And that becomes now a subpopulation-based recourse approach. And of course, depending on the causal model that you have and the uncertainty you have about the background variables corresponding to Edward, you're going to have uncertainty in your predictions as well, right? But that's really the best you can do. Questions? Yes.
So at some level, you're imagining a world where you go to the bank, you get rejected, and then they tell you how to get your life back on target.
Sure.
Oh yeah, you want to buy this multi-million-dollar mansion? Take this action, right? I mean, it seems a little bit like high onus for that bank to be able to like explain to people like how to, this is how you have to conduct your life in order to buy this mansion, right?
Sure, absolutely.
I mean, so yeah, maybe you can just comment on that. I mean, is it too high of a bar, right? I mean, in very complex systems, it's like, I mean, I'm just imagining that scene in like one of the Marvel things where the guy calculates, there's like a 1 in 4 trillion odds if you survive this, and he goes off and does it. Like, ostensibly, algorithmic recourse has to offer that 1 in 4 trillion dollar option policy. Like, okay, it's very slim, but if you exactly navigate the situation, you might be able to buy this mansion.
Yes, by no means is this talk going to claim that we've solved recourse. No, actually, the more we solve, the more problems actually show up. And one of them is that, how do you manage the expectations between stakeholders, and how do you actually get the stakeholders to play fair? Let's say that there exists a number of recommendations at a bank, assuming they've done all of these steps, made good assumptions, made good inferences, blah, 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 and we'll see some of the problems in later slides. Assuming there's a set of recommendations that the bank has to offer to the individual, which one do they choose? Of course, they're the bank, right? They're gonna choose the one that goes nicely with their bottom line. But is that the one that's beneficial to the user? Probably not. Is there a risk associated with giving a lot of recommendations? Absolutely, and we'll see that in the new slides. It's a very hard problem. So far, what we've seen is that without an assumption of causality, you're definitely wrong. With an assumption, you're just a bit less wrong, but we still have a ways to go with it. Does that make sense? I know it doesn't answer your question, but
Yeah, no, it's very complicated.
Okay, to summarize what we've seen so far, so we looked at deterministic recourse under the assumption of full specification of our structural equations. This gives us a point estimate as to where Edward would be. If we start to move towards lesser assumptions, lesser strict assumptions about the causality, the causal model, and we assume additive Gaussian noise models, then we get an individualized but probabilistic version of recourse. And if we don't even assume that, then we have to go down one step in our causal ladder, and now we have interventional distributions, which is called subpopulation-based recourse. So to summarize the first question, no, counterfactual-based recourse actions do not yield feasible or optimal actions for recourse, and instead we need to reformulate the optimization problem to explicitly have causal assumptions that would yield either deterministic or probabilistic versions. Okay, second question, this will probably be a bit faster. How does providing recourse affect other stakeholders? So going back to the beginning, we said that besides Edward, which was very much centric to our optimization problem here, there exists other individuals like researchers and developers like yourself, owners and deployers like the bank, examiners and regulators like Government Canada, and data subjects like us and myself and Dan who want to get alone. Now, in such an environment, besides recourse, we should be thinking about both the robustness of recourse, security and privacy issues that might arise, fairness issues, and strategic manipulation and strategic behavior. And we have a couple works which only really just scratch the surface along these lines, and I'll present the problems. So take this situation here. Let's consider now a decision boundary that says anything to the right of x equals 0 is granted a loan, and anything left of it is not granted a loan. We know from our population that we have two different distributions of individuals, Edward and maybe Edward with a tie, I don't know, two different distributions. And this is the structural causal model that represents these distributions. So we have U of A as a binary variable, in this case corresponding to whether the person is wearing a tie or not. And then X is some multiplicative version of a Gaussian noise distribution times 2 minus A, and then the decision by the bank is the sign of whatever value. Now, in such a very simple situation, this you might say is a fair classifier. Based on various definitions of fairness, you might say that, yeah, actually 50% of the population of both of these distributions are denied, and that's a fair predictive classifier. But unfortunately, it's not a fair classifier in terms of recourse, because as you might notice, the average distance from one of these populations is larger to the decision boundary is larger than the average distance from the other population. And so we have a whole rich literature of fair prediction, but almost none about fair recourse. And these two do not imply one another. So which is correct? Is it sufficient to say that we have a fair model and just go on with our lives, even though we know that some subpopulation will be penalized because of whatever distribution they have? We do explore some solutions like restricting the inputs to the classifier. Of course, that's going to cost the bank more, or adding further constraints to an already very complicated and full of assumptions optimization problem. It's going to jeopardize the feasibility of it. Or doing some representation learning, and that's going to come with its own assumptions. So we don't really have a solution, and it's certainly an open problem. Now, besides fairness, we can also look at robustness, right? Let's say you go to a bank and they give you a recommendation, but by mistake, you filled out some part of the form, just slightly off. So if you have something just slightly off in your inputs, does the recommendation turn out to be completely different? So really the question is, how does one safeguard against such small changes? And as before, we have some potential solutions, like maybe we train a regularized classifier, right? The decision boundary now looks a bit different with the problem that now it's going to cost everyone more. Or we, again, considering the optimization problem, that's going to jeopardize feasibility. And so one question that comes up is, as we think about giving recourse to Edward alone, who else within this environment gets affected, and who else should be bearing the cost of recourse? And going back to the example that Dan asked about, which is the bank has several options, and which one do they choose? Does the bank have to incur some costs? Do they maybe let go of some profit in order to be explainable and interpretable to individuals? So let's maybe very rudimentary draw out what the cost would be. If we have non-robust recourse that's somewhere here, it's not costing the individuals much, it's not costing the institution much, but of course it's not robust. We could introduce robust recourse. This is going to cost individuals like Edward a lot more. We could regularize the classifier. It's now going to be distributed amongst them somehow. It's going to cost everyone more. But there's also another axis that's missing from this diagram. And that is that we all live in a society governed by governments that sometimes provide us with subsidies, right? Maybe we introduce that axis as well, and now we call it societal recourse. And so these are all very much unsolved problems. And as you can imagine, we're now veering off into a non-technical domain. And answering this, again, I think if you take one thing away from this talk is that when you get into the nitty-gritty of this, we can, as computer scientists and computer engineers, give some technical solutions, but they're going to fall short in so many ways when you apply them to practice. So we need to invite everyone to the conversation in order to actually make progress on this. One final problem I'll leave you with is a model stealing problem. So imagine now you have this decision boundary. You have Edward that's here, and he's given a counterfactual explanation, and counterfactual explanations intuitively mean the closest point on the other side of the decision boundary, right? So he's given an explanation like this one here. Now, a question that comes up is, what does a counterfactual explanation actually reveal? If we know that this is the closest point on the other side of the boundary, then the next step is to infer that everything within the ball centered at Edward with the radius of the distance between them is not on the other side of this boundary. Yes? No? No? It's following along? So if everything is not on the other side, then everything shares, the same classification. And if everything shares that, what if your friend, Eduardo, whatever, is also here? Oh, now you know that Dan's also denied. I'm denied, Dan's denied, everyone else is denied. Is that a violation of privacy? Perhaps. How do we deal with that? I don't know. We don't have an answer for it. Now, probably more worryingly is not just, another individual that might be close by to you according to some metric, but what happens if you now have multiple counterfactual explanations? Now you're starting to fill up the entire space. And so you can infer the entire, not only other individuals' features, but the entire decision region of the bank. Does that mean you can now you're able to game the system? Of course. This seems like a contrived example, but model stealing, anyone work on model stealing? It's a very interesting problem. From 2017, they did tests on models hosted by AWS, and with a query budget of less than $10, you could, with above 90% fidelity, extract and recreate a model that was hosted on AWS. Now, of course, models cost a lot, sometimes in the millions, sometimes in the billions, right? If you can't even infer and steal some of their behavior, what does that tell us about everything we know about model security? Right, so, and then we want to provide explanations, but then there's a risk, there's a trade-off when you provide explanations. Anyways, how does providing recourse affect other stakeholders? Offering fair and robust group-level recourse requires a delicate balance. Yeah.
So, like that's the other person determines something like how, like we may know why the first one didn't get the loan, and we explain that. But the second one, we are saying, okay, here's the close one, but I assume that the model has many features. It's not easy still to steal the model, or I cannot also understand the relation with privacy of people, because everything is not revealed. You just know one person hasn't got the loan for this reason, and that person had many features that they are not very closely matched to other people.
Sure.
So I think it's still far from detecting the model. So
You're right. You need to have an understanding of what the metric system is within the space to know that you're actually close by to one another. But if you have an understanding of that somehow, then you know that this is your distance to the explanation that's given to you, and this is the distance to your friend, and if one is less, then you're in the same.
in low feature space, it's probably much easier. If we have many.
Of course, one thing is with dimensions, then maybe you obfuscate the privacy risks. and then you add on some other risk of actually being able to give a feasible solution for this. It's a very difficult problem to try to manage all of it at once. For the case of model stealing, I think it's a bit more obvious, right? If you have, for instance, this is a nonlinear decision boundary by purpose, but if this was a linear decision boundary, we'd need one query to steal the model, right? If you have an optimization problem giving you exactly the minimum point on the other side, then you get the normal to that plane, and one query is enough to steal the whole thing. And that's why purely linear models are not recommended in practice either if someone's trying to game the system. Did that answer your question? Other questions? Okay, right. So if we want to offer fair and robust recourse across stakeholders, then we need to be careful. And I guess that's a takeaway. To summarize what we've said so far, counterfactual explanations from existing methods do not imply consequential recommendations. Recourse can only be guaranteed if you have perfect knowledge of the world. Of course, we don't have that, so we need to resort to probabilistic solutions. In the probabilistic solutions, there's going to be a trade-off between the strength of assumptions we're willing to make, as well as the level of individualization. We talked about the diversity in stakeholder needs, and I've maybe now twice emphasized the need that solving these requires a cross-disciplinary expertise of a panel of both technical and social science. Dan mentioned at the beginning that this recourse is not an abstract, thing that we're trying to solve. It's actually now since 2023 at least, in the Treasury Board's Directive on Automated Decision-Making. You scroll down, recourse, providing clients with any applicable recourse options that are available to them to challenge the administrative decision. And so it's a real problem there, and we don't really have solutions. And this is a directive, it's not a law, but things are moving so fast that if it turns into law and we don't have solutions, then I don't know really how it can be enforced or how it can be resolved. Just a few ideas about future work if you're interested. What remains to be done? We've assumed so far that we have an underlying model, which is a classification and regression model, but recourse can be applied to a number of other systems like matching or scheduling. Let's say you want to find a hot desk here, right? You have a scheduling system, you don't get the one that you like. How does that work? How do you gain recourse in it? We've assumed so far that we're working with variables of meaningful concepts like age and eye color and bank balance, but we might not have that. We might have abstract concepts. How do you offer recourse over abstract concepts? We've assumed that recourse is an interaction, which is actually a single step recommendation. But as we know in the world, you take an action, some other agent takes an action, and so it's more dynamic, and you might want to be giving multi-step or conditional interventions. We've talked extensively about stakeholders. The problem is not resolved by any means. We've really only scratched the surface. And finally, recourse might be needed to be given as a discussion because there's world knowledge that we might not be able to yet formalize, like individualized cost functions, like Dan was saying, or infeasible actions, or whatever it is. And so recourse might itself be, or explainability as a whole might be a collaborative discussion rather than anything else. And finally, I guess it need not be said, but just for the sake of completeness, recourse is not just about Edward and applying for a loan. Anywhere you have consequential decision-making, which is a lot of very important places, you're going to have to deal with recourse. And with that, I thank you for your time.
So we have time for questions. There's a mic hidden somewhere here. Yeah, can someone help me out and pass that to pass that back?
Thank you for your talk. So we talked about how these interventions could be done and this understanding how the decision is made. One question I have is that we have to have that model. We have to have like a causal graph, and in terms of like constructing that causal graph, what are the challenges and what process should be done in general?
Okay, that's a great question. Causality in machine learning has two subfields of research. One is called causal inference, which says if I assume this is something about the causal model that I have, either in full or in partial assumptions, then how do I understand the interventional distributions and how do I understand the counterfactual distributions? Conditioned on the assumption of causality. Now, another subfield of causal inference is called causal discovery. And causal discovery is exactly that I have some observations about the world. how do I infer which variable is, affecting which other ones in which way? And there are some unfortunate impossibility results that exist. One being that if you only have observational data about the world, then you can't infer anything really about causality. Or you can, but up to very crude and coarse levels, and they call that a Markov equivalence class of models. So the simplest example is a two-variable causal world, like let's say temperature and elevation again. If you take a big data set, hundreds of thousands of rows with these two columns, you cannot say which one causes which. And the only way to actually do that is to then start to intervene on the world, which is go for a hike, and then you're like, oh, it's actually getting colder, so maybe it's in this direction, right? So even for a two-variable system, causal inference has impossibility results, and it's hard. Now, who here has heard about RCTs, randomized control trials? Okay, right, RCTs, good. RCTs are the gold standard in healthcare, in econometrics, in a lot of fields for understanding the link of causality. And the way that RCTs work, just so you intuitively understand, is that you take one population, and at complete random, right? Close your eyes, throw a dart. At random, you select one portion to be a control group and one portion to be a treatment group. And it's very important to be at random because you want to break all the links that exist. And then you go through your study, and then you see, oh, what was the difference in the output target that I was looking at? And that's one way of maybe getting a better sense of the causal link.
Yeah, but like there's a challenge when you do interventions. Obviously, the Simpson paradox comes into play. Okay, how are we going to intervene? Like, how are these factors going to come into play? Like, we can see it in nutrition. Like, if I take this, it's good or bad. Like, we can experience some of those challenges.
Yes, Simpson paradox is just solved to injury in that case. It's hard, and I don't want that to be the takeaway that causality is hard, but I mean it is. And you've seen throughout, I'm saying, we need to make this assumption, and we know it's wrong, but not making the assumption is also making an assumption that the world is independent, and that's definitely wrong, right? So, and if you're writing causality papers also, I think this is what I tell my students as well, is that you can do your best to come up with a set of assumptions and do your best to do inferences on those set of assumptions and have a solid paper. But if you get someone who disagrees with the foundation, which is your assumptions, then that's where you got to work on. You have to see eye to eye for the inferences to then make sense. But that's why, it's difficult to do causality papers.
I just have a second question. So I was also curious as to how randomness comes into play, when modeling these causality pairs, because for example, like job hiring, okay, we can have two identical cases. For one person, it gets a job, the other person doesn't get a job.
Yeah.
So how does this randomness is formulated into these ones?
I didn't quite understand the randomness in your example.
So okay, not everything is based on qualifications. Like I don't know, other factors can come into play. Like I don't know, like the person that is hiring might be in a good mood. Okay, we can model it as that kind of factor.
Right. So in this example that you said, randomness plays into the classifier itself. Here we're assuming the classifiers are fully deterministic, right? So, but you could throw that in the mix and complicate it further, making it a bit more realistic.
That was my question. How can we bring it into?
So in the case of the probabilistic recourse that we talk about, the optimization problem that wasn't shown on the slides is trying to move an expectation of an intervention or counterfactual distribution on the other side of the boundary. Then there's an H theta there. Your H theta would become probabilistic as well. So it would be a nested expectation.
So we take multiple interventions and that limits the expectation
yes.
To
yes, we actually do a Monte Carlo approach, taking multiple interventions, assuming what it would look like, and it's quite involved. Yeah, no problem.
All right. Any more questions? Maybe I'll ask you a quick one before we let you go. So, an alternative to this entire paradigm is to say, just release your decision boundary, because then it's the individual's problem of figuring out how they can navigate to the other side, right?
Yeah.
Because right now it's saying you're not gonna release this decision boundary, and I have to tell you how to find the other side.
Yep.
And then you raise this interesting question like, well, how does what I tell you about how to get to the other side reveal about the decision boundary? You could just say, well, for some things like loans, you have to reveal the decision boundary.
Sure.
And now the problem of navigating to the other side is the individual's problem.
Yep.
So I mean, I imagine there's been thought on this, so maybe you can just summarize. Maybe.
Surely, I mean, we can ask also the audience, what's the problem with revealing the decision boundary in full? There's certainly problems with it, right?
Yeah.
You could have bad actors in any system that, will then try to game the system. And I mean, loans, maybe who cares? It's profit anyways, but like, pre-trial bail, which is releasing someone from jail, yeah, you don't want people to game that system, right? It's hard. I mean, we're already assuming that the models are actually accurate and fair and all that, which itself is a, a high bar, but we don't want to worsen things. So anyways, lots of open problems. If you're interested in any of this, come chat with me or the broader agenda, and thanks for your attention.
Right. So thank Dr. Karimi again.